Welcome to this lesson on real gases. In previous lessons, we studied the ideal gas law and how it perfectly describes gas behavior under certain assumptions. However, in reality, gases don't always follow these ideal conditions. Today, we'll explore when and why gases deviate from ideal behavior, helping you understand the limitations of the ideal gas law and what happens in real-world scenarios. Let's quickly recap the ideal gas law. The equation PV equals nRT relates pressure, volume, number of moles, the gas constant, and temperature. This law works beautifully under certain conditions, but it's built on two major assumptions. First, it assumes that gas molecules are point masses with absolutely no volume. Second, it assumes there are no intermolecular forces, meaning molecules don't attract or repel each other at all. The ideal gas law rests on two critical assumptions. The first assumption is that gas molecules have zero volume. We treat them as infinitely small point particles that take up no space whatsoever. The second assumption is that there are no intermolecular forces. The molecules neither attract nor repel one another, they simply move independently through space. While these assumptions simplify our calculations tremendously, they aren't always accurate for real gases. Here's the reality check. Real gases deviate from ideal behavior under certain conditions. In the real world, gas molecules do have volume, and they do experience intermolecular forces. These factors become significant when gases are subjected to extreme conditions. Understanding when these deviations occur is crucial for accurately predicting gas behavior in industrial processes, chemical reactions, and natural phenomena. Real gases show significant deviations from ideal behavior under two main conditions. First, at low temperatures, molecules move much slower. When molecules slow down, the intermolecular attractive forces become significant because molecules spend more time near each other. Second, at high pressures, molecules are forced much closer together. When molecules are compressed into a smaller volume, their own physical size becomes important, and we can no longer ignore the space they occupy. To account for real gas behavior, Dutch scientist Johannes Diederik van der Waals developed a modified equation. The van der Waals equation includes correction terms to fix the problems with the ideal gas law. The equation reads, open parenthesis p plus a n squared divided by v squared close parenthesis times open parenthesis v minus nb close parenthesis equals nRT. This equation adds two correction factors that account for intermolecular forces and molecular volume. Let's understand the two correction terms in the van der Waals equation. The pressure correction term, a n squared divided by v squared, is added to the measured pressure. This accounts for intermolecular attractions that reduce the pressure exerted on container walls. The volume correction term, nb, is subtracted from the total volume. This accounts for the actual physical space occupied by the gas molecules themselves, giving us the free volume available for molecular motion. The van der Waals equation uses two constants specific to each gas. The constant, A, measures the strength of intermolecular attractions. Gases with larger, A values have stronger attractive forces between molecules. The constant, B, measures the molecular size or excluded volume. Gases with larger, B values have bigger molecules that occupy more space. Different gases have different values for A and B, reflecting their unique molecular properties. Interestingly, even real gases can behave ideally under the right conditions. At high temperatures, molecules move so fast that intermolecular forces become negligible. At low pressures, molecules are so far apart that both their volume and intermolecular forces become insignificant. Under these conditions, the correction terms in the van der Waals equation become very small, and the equation simplifies back to PV equals nRT, our familiar ideal gas law. Here's the key takeaway from this lesson. Real gases deviate from ideal behavior at low temperatures and high pressures. These deviations occur because real molecules have finite size and experience intermolecular forces. The van der Waals equation provides a more accurate model by correcting for these factors. Understanding when gases behave ideally and when they don't is essential for practical applications in chemistry engineering, and physics. Remember, the ideal gas law is a useful approximation, but real gases require more sophisticated models under extreme conditions.
If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.